Hi guys, we are going to just do a short video of the Exam 3 review questions, and I'm just going to jump right into it. So hopefully you've pulled it up or printed it out. So the first question, a gas in a closed cylinder undergoes a particular chemical reaction releasing 79 kilojoules of heat. My mind is immediately looking at that verb, releasing, to its surroundings and doing 18 kilojoules of work on its surroundings. Calculate the change in internal energy. So change in internal energy is delta E. That means internal energy, that means change in. And the equation that you would use for this is Q plus W. The key here is I've been given the amount of heat and the amount of work. And the key here with this equation is the signs. So you have to be really careful about the signs. When it says it releases 79 kilojoules of heat, if it's releasing heat, that is a negative. That is an output of heat. And we'll just put in 79 kilojoules for Q. Negative 79 kilojoules. So the system releases, or the gas is the system, that's the thing you're studying, releases 79 kilojoules of heat, and it does 18 kilojoules of work. Doing work is also an output, as opposed to having work being done on you, which would have been a positive. But doing work is a negative, and that would be negative 18 kilojoules. And when we put those together in our calculator, negative 79 plus a negative 18, which you get to the answer of negative 97 kilojoules, and that would be the answer. So with this equation, just be very careful of the wording, because you have to choose whether you're going to use negative numbers or positive numbers. So you have to be very careful of that. So question number 2, calculate the energy of a photon of light. As soon as I see that, I immediately think of this equation. E photon equals Planck's constant times frequency. So I'm trying to find the energy of a photon of light, and they've given me a wavelength. So 900 nanometers is the wavelength. I'm going to immediately want to put that into meters. So you can do that by remembering that in every 1 meter there are 10 to the 9th nanometers. So you can divide by 10 to the 9th. 9.0 times 10 to the minus 7th meters. Okay, so the reason I put it in meters is because I need frequency. I'm given wavelength. So anytime you are trying to get frequency from wavelength, you need this equation. So we're eventually going to use this one, but you got to use this one first. C is the speed of light, and that's 3.00 times 10 to the 8th meters per second. That is why I needed my wavelength in meters, because I'm going to need to be able to cancel that meter unit. So that would be times frequency. And so you would just do speed of light, 3.00 times 10 to the 8th meters, and you're dividing by, and any time that you're dividing, put the whole scientific notation number in parentheses. You got to be very careful with how you enter these in your calculator. I'm getting a frequency, and you'll notice the meters are going to cancel each other out when I divide by it. So the frequency is going to have a unit of s to the minus 1, which is the same thing as a hertz. So 3.33 times 10 to the 14th, s to the minus 1, or I could have said Hz, hertz. Anyways, but that's the frequency. We're really trying to get the energy of a photon. So H is Planck's constant, and I give it to you in the question, the value of Planck's constant. So let's just times the frequency, which we just got, times Planck's constant, and make sure we get the right answer. Planck's constant has a unit of joules times seconds. And when you times that by a unit of s to the minus 1 from the frequency, those two units are going to cancel, because one's on top and one's on the bottom. So your answer will end up being in joules, and I'm getting 2.21 times 10 to the negative 19th joules. I rounded it to 3 sig figs, which would make sense based on what was given in the problem. And that is the right answer. So if visible light is between 400 and 750 nanometers, identify which type of radiation this photon is. Okay, So this is just a little tiny question on the electromagnetic spectrum. Remembering that light can come in many different wavelengths and different frequencies. And visible light right here is in the middle. Visible light. And it says it's from, and it's true, visible light is around between 400 and 750 nanometers. So really, the 400 nanometers would be the shorter wavelength. And the 750 nanometers would be the longer wavelength that I've drawn here. So I'm drawing it where the long wavelengths are on the left and the short wavelengths are on the right. Like that's how I did it in the video. So if visible light is between 400 and 750, because those are the longer ones, it's saying what would this one be? And we, in the question, saw that it was 900 nanometers. So it's going to be the one that's directly lower in energy from visible, and that it's infrared. So 900 would fall right past visible. And by the way, it's called infrared because the visible light, remember, is in the order of Roy G. Biv. So infrared is right below red. Ultraviolet is right above violet. Okay, that would be that question. So now let's do the next one. We got a reaction. It's a thermochemical equation. So 2MgS plus O2 gas yields 2 magnesium oxides. I don't have the phase label there, but it should be a solid. And then the delta H is negative 1204 kilojoules. So that means that this is an exothermic reaction. And I know that just because it's a negative sign of the delta H. So that's part A. Part B, how many grams of magnesium would be required to produce 556 joules of heat according to this reaction? So remember, the key here, if you look at this question, there's really only one number in the question, and it's 556, what does it say? Joules of heat. The key here is that when you have a chemical equation, thermochemical equation, which has the delta H information to the right, you can construct conversion factors, kind of like mole-to-mole ratios. Like remember, for every 2 moles of this, you would need 1 mole of that. For every 2 moles of this, you'd need 2 moles of that. Kind of incorporate the heat into that. For every 1,204 kilojoules of heat released, you'd need 2 moles of this. For every 1,204 kilojoules of heat, you'd need 1 mole of that. You can relate the heat that's released to the molar amounts of the coefficients. So really, we just need to kind of use dimensional analysis. So let's turn it into kilojoules so that we can actually use this conversion factor. So I'm just going to create a conversion factor that says this. I am going to get 1,204 kilojoules of heat released whenever I react. And what's the question about? It's about grams of magnesium. So we want to relate this to this species. So for every 2 moles of magnesium. So you relate the heat to whatever one the rest of the question is about. Make sure you do the coefficient is the number of moles. I dropped the sign because I didn't include it here. It's either you just have to be consistent. When they wrote required to produce 556 joules, technically producing is an output of heat. So if you do it there, you should do it here as well. But I just kind of considered it like an absolute value. And the thing is that if you include one and not the other, what you'll end up doing is getting like a negative mass, and then you'll know, just get rid of the sign. You can't have a negative grams. But speaking of grams, we need to put this into grams. So gram per mole, 24.31 grams per mole for magnesium. And that should do the trick. So let's see here. Like I said, if you get a negative of your gram, just don't include it, because you can't have a negative mass. And I am getting, for an answer, take it out of scientific notation, 0.02245, and then since that has 3 sig figs, this would bump up to 5. So I'm getting 0.0225. 0.0225 grams, and that is the answer. Okay, let's move on. So All right. If 10 kilograms of liquid water at 24 degrees C absorbs this much heat, what will its final temperature be? So equations where you are dealing with relating the amount of heat that's coming in or out to temperature changes, that is this guy. This equation is what you're going to use anytime you're relating the amount of heat that's either coming into a substance or out of a substance and relating it to its initial or final temperature or its overall change in temperature. Okay, so this is really a plug and chug type thing. We are absorbing 904 kilojoules of heat. That means the amount of heat is a positive number. It's coming in. I am going to go ahead and put that into joules, 904,000 joules. The reason I'm going to put it into joules is because the specific heat of water is going to have a joule unit. That part is going to have a joule unit. So you have to make a match. Mass, 10 kilograms. Same thing. I'm going to put that in grams. That's 10,000 grams. For the same reason, the specific heat is going to have, we have 4.18 joules over gram degrees C. So we need those units to cancel. So if they don't match, you got to make a match. And then we're solving for, what are we solving for? Final temperature. But we have initial temperature. So what I would do is just solve for delta T. I would solve for delta T first, and then we'll do the final temperature in a minute. So let's figure out what the change in temperature is. All right, I'm getting that delta T is equal to 21.63 degrees C. Okay, delta T is equal to T final minus T initial. And I was given the T initial, it's at 24.6 degrees C. So now really this is the equation that I'm working off of. So I have delta T, and I'm setting it equal to T final minus T initial. So I just need to solve for T final, which is add T initial to both sides. And you should get 46.23 degrees C, which would round to 46.2 with the sig figs. 46.2 degrees C. Notice my sig figs are going to be determined by how many decimal places, because this is an addition. But that's not, we won't worry about that too much. So 46.2 degrees C. Moving on. Calculate the standard enthalpy change for the following reaction using standard enthalpies of formation. So, have a reaction, MgOH2, solid, yields MgO, solid, plus H2O, liquid. And we are trying to figure out the standard enthalpy change. So that's how much, that's really just the enthalpy change. Standard just means you put a little circle up there. That's not a hill that you need to die on. It basically just means that it's done under what's called standard conditions, which is like, for this type of context, it's 1 atmosphere and room temperature, not 0 degrees C, but it's fine. It's not a major thing for this thing here. So we are trying to figure out that number. One of the ways you can figure out that number is to use standard enthalpies of formation. So that is the thing where standard enthalpies of formation are these little things that look like that. Standard enthalpy of formation. And what we'd have to do is look these up in the textbook. So you would go to your appendix. Now, on a test, I would just provide them to you. I'm not going to be requiring you to look things up during the test. So I would just provide them to you. So magnesium hydroxide solid, standard enthalpy of formation. In appendix 2, I'm getting negative 924.5. And that is kilojoules per mole. Magnesium oxide solid, negative 601.6 kilojoules per mole. And H2O liquid, that's under oxygen. negative 285.8 kilojoules per mole. This is the deal where you do have to consider the coefficients. You do have to, if this is a 1, which it is, you do have to times it by 1 mole. I mean, obviously that's not going to affect your number. It does get rid of the mole unit for you. But for instance, if that was a 2, that would affect your number. So make sure by habit, you always times these by your coefficients. And that really is the way that you're going to get rid of the mole unit. Because remember, the coefficients are the number of moles. So now I divide between my reactants and my products. I sum total both sides, because the equation we're using is this one. To get the delta H for a reaction, we're taking the sum total of the standard enthalpies of formation of the products, and we're subtracting the sum total of the standard enthalpies of formations of the reactants. So let me get the total for the products. Negative 887.4 kilojoules. And then the reactants, that doesn't change. Now you have to make sure you keep the signs very organized. This minus that. And I'm getting an answer of 37.1 kilojoules, which is the right answer. So be very organized with your signs. Okay, next problem. So with that one, just make sure that you consider the coefficients. Don't forget about how that would affect the number. And then also remember that I might not give you the standard enthalpy change for a element in their standard state. So like you should probably know that iron, his standard state is 0, or sorry, his standard state is solid. That's the state he's in at room temperature and 1 atmosphere. So therefore his standard enthalpy formation is 0, and it is, as is, you know, oxygen gas, something like that. Some of these are, you should just know. You should know that mercury is a liquid at room temperature. You should know that, you know, hydrogen is a gas, nitrogen is a gas. Not too many of them. Iron, because you're familiar with iron, copper, so that's obviously a solid at room temperature. That's his standard state. Okay, moving on. The complete combustion of acetic acid releases that much heat per mole. Write a balanced thermochemical equation. So acetic acid, combusting it. That means reacting it with oxygen gas. It only contains carbon, hydrogen, and oxygen, which means it will only contain or only produce these 2 compounds. And now I just need to balance it. So without looking at it, I always balance carbon first, then hydrogen, and lastly oxygen. So 2 carbons, I can do that with this. 4 hydrogens total, I can do that with this. Let's see if that works out. And now oxygen. So I have 6 oxygens on this side, and I can get 6 by putting a 2 right there on the left side. So that should do the trick. Now, that's the balanced chemical equation. This asks for a balanced thermochemical equation, which means it must contain the delta H to the right. And it releases this much heat, which means it's exothermic. So I need to have the sign as negative. Right there, negative 871.7. If it was positive, it would have said something like absorbs this amount of heat or requires this amount of heat. Draw an enthalpy diagram. Okay, so enthalpy diagram. Enthalpy and different things. I usually write reaction progress. You could write reaction coordinate. But it's basically you just taking this straight thing and putting it on a up and down based on whether it's exothermic or endothermic. So this is exothermic, which means that your reactants had higher amounts of enthalpy internally, which is really just another form of energy. So you would write the reactants. I would accept that. I mean, your test is going to be multiple choice. So anyhow, if it's exothermic, the products have a lower amount of energy in their bonds, you know, in their in themselves. And so therefore all that extra energy, which used to be there and now it's not there, that's got to come out. And I mean, you don't have to include this part, but that's why it releases heat. So at least it's this downhill concept for exothermic. And endothermic would just look opposite. Reactants would be lower, products would be higher. And that's why heat needs to come in from the outside, from the surroundings, to push you uphill and give you all that extra energy that gets stored in the compounds. That is a enthalpy diagram. All right. How many unpaired electrons are in arsenic? Okay, arsenic. Go to your periodic table and see how many electrons it has. So it has 33 electrons. So there's different ways to do this. If you want to just read it, if you've gotten pretty good at reading your electron configurations, that's fine. You could do that diagonal rule that we talked about. But either way, you would end up with an electron configuration that looks like this. So that's 10, 20, 30. And then the last three would be in there for P3. The question is asking me for how many unpaired electrons. And so I really could just kind of zero in on this part of the orbital diagram, which is the 4p sublevel. And remember, according to Hund's rule, those electrons need to fill up one at a time. And so therefore, the answer is 3 unpaired electrons. Which orbital sublevel are they in? They are in the 4p sublevel. Sublevels are basically, this is the 4p sublevel, that's the 3d sublevel, this is the 4s2 sublevel, this is the 3p6, and so on. You get the point. Whereas, so that's sublevel or subshell. Whereas, like, when you consider, you know, everything that has an n number of 2, for instance, that would be the principal energy level 2, all of them. So it would contain 2 different sublevels. And these are called, in the old school way, called shell 2. Anyways, that wasn't part of the question. Identify the 4 quantum numbers of the very last electron in arsenic's orbital diagram. So this one. So 4 quantum numbers. N is equal to 4. That's this number. L is equal to 1 because p orbitals always have an L value equal to 1. ML is, remember, MO can be -1, 0, and +1. And most people would just label it in order. So you would say +1. And then the MS value is spin up or spin down. And by convention, if you only have 1 electron, it would spin up. So that should be +1/2. All right. Next question is electron transitions. Probably a little bit one of the harder types of questions. Let's take a look here. If an electron transitions from n equals 1 to the n equals 4 energy state, okay, so we have a hydrogen atom. Here's its nucleus, 1 proton in its nucleus. It's got n equals 1, n equals 2. And remember, they get closer together as you move farther out like an onion. So you have an electron. It's going from n equals 1, which is the first orbital, or not orbital, but like they call them stationary states. N equals 1 going up to 2, 3, 4, this one. Yeah. So this is a jump up. Will that be accompanied by the absorption or emission? Okay, definitely absorption. To get an electron to jump up and basically go higher in energy, where it really doesn't want to be, you're going to have to supply a photon from outside. So that's the absorption of a photon. Whereas opposed to a fall back down from high to low, that photon would come out. You'd have an emission of a photon. So anyways, absorption. And what will the wavelength of that photon be? So to get the energy of the photon that's either released or absorbed, it's this equation. All right, and so we are just calculating this equation, and n final, the final state is 4. So 4 squared is 16. minus the initial state was 1, and then putting that in your calculator, we should be able to get the answer. So I would always do this part first. So this is 1/16. I just put in 1 divided by 16, and then I minus 1. And I get the answer, and then I'm timesing it by this. Notice the unit is joules, and I'm getting 2.04 times 10 to the negative 18th joules. See if that's what I got last time. Oh, I used 4 significant figures. I don't know really why I did that. I would just use 3. Oh, I know why. Because I didn't want to round too much, because the final answer was wavelength. So that's fine. I'll put it back in there. This is not going to be a major, the sig thing will not be where you get it wrong. If you do, that's not the issue. So that's the energy of the photons. You notice that it is positive. The number you get is positive because it was an absorption of energy. That photon came in. Now we are trying to get the wavelength. So here you would that's the energy of a photon. If I set that equal to h frequency, that E photon equals h times frequency, I can solve for frequency by just dividing by Planck's constant. So I'm going to go ahead and divide by Planck's constant. I'm getting a frequency equal to 3.084 times 10 to the 15th, and it's going to end up being s to the minus 1. So this equation here is just that early one, E photon equals h times frequency. Now we have the frequency, and now if I want wavelength, I come back to this other kind of handy-dandy thing, which is the speed of light and equals wavelength times frequency. So if I do speed of light divided by frequency, I should get my wavelength. And I'm getting a very tiny number, which would make sense. I'm getting 9.7273 really, times 10 to the negative 8. The unit would be meters because that's the length unit that came with, I know I'm skipping some things, but not really. It's the unit that came with speed of light. And I think, am I asking it for, I didn't ask for it in nanometers, but first of all, visible light is usually in the nanometer range, and you'll see that that is the appropriate unit conversion there, because in every 1 meter there are 10 to the 9th nanometers, and that will put it in a much more doable number. So let's times by 10 to the 9th. I am getting 97.3 nanometers. And that would be the answer, 97.3 nanometers. Okay, last one. What are the 4 different quantum numbers? Include their names, abbreviations, what they describe. So I'm not going to do that. Just that's in the chapter, actually chapter 8 video. So you could study that on your own. Which of these combinations of quantum numbers are possible? That we can do. So not every combo is even possible, because remember this whole concept of possible values was a really big deal with Schrodinger's equations. So we've got 2, 2, negative 1, plus 1/2. 1, 0, 0, minus 1/2. 4, 1, negative 2, plus 1/2. 3, 2, 0, 0. Okay. Impossible or possible. So if n equals 2, and n can be 2, so let's check that. The first one cannot be a 0. If n equals 2, then L can be 0 and 1. So this is impossible because of L cannot be 2 if n equals 1. If n equals 2. If n equals 1, L can be 0. That's fine. And if L is 0, ML can also be 0. It can actually only be 0. And you can have a negative 1/2. You can spin down. So that is possible. If n equals 4, which is fine, L can be a 1. It can actually be 0, 1, 2, or 3. If L is 1, ML can be negative 1, 0, and positive 1. So this is no good. This is impossible. And then if n equals 3, L can be 2. If L is 2, ML can be -2, -1, 0, +1, +2. So this is fine. Oh, but this is no good because MS, the spin quantum number, cannot be a 0. There's only 2 possible values, and that is +1/2 and -1/2. So hopefully that is helpful. That's definitely not all that you should be doing to study for the test. Whoops. But it will at least proceed you farther. So have a good rest of your day. Good luck studying.